We're going to solve polynomial and rational inequalities. It's very important for us to understand that we need to get our inequalities in the form where we are greater than 0 or less than 0. That includes the greater than or equal to 0 and the less than or equal to 0. We always want 0 on one side of our inequality. So if we remember that one important fact, it's going to save you a little bit of aggravation down the line. So I'm going to show you with an easier problem that you learned in early algebra classes why it's important and how we're going to solve these just a little bit differently. I'm going to distribute the 3. I get 3x minus 12 is less than or equal to 2x minus 6. I'm going to follow this step and I'm going to get my inequality where I have 0 on one side. So when I subtract 2x from both sides, I get x. And when I add 6, I get minus 6 is less than or equal to 0. Now, our first inclination is let's add the 6 over to the other side. And you can certainly do that when you have a linear expression on one side of the inequality. However, I want to set the foundation for where we're going to be going. So once you have this situation where you have everything on one side of the inequality, you're going to make sure that you have factors. So what I've done is I've created a factor by putting parentheses around x minus 6. You're going to use the zero product property, and you're going to set each factor equal to 0 so that you can find critical values. I also call them critical numbers. So critical values, critical numbers, numbers slash values means the same thing. So x equals 6 is a critical number for this problem. So we create our number line where we have negative infinity on the left, positive infinity on the right, and somewhere in between we have our critical number 6. We have two intervals now. We have negative infinity to 6, and we have 6 to infinity. We want to test each interval to see if its truth value satisfies the inequality. So its truth value, if it's true, if you pick a number between negative infinity and 6, let's say 0, and we plug it into, I'm just going to plug it into the original because that's what I'm going to be doing later on. So we're going to plug it into the original. When I put a 0 in, I get 3 times negative 4 is negative 12, right? So negative 12. Actually, let me write it right here, negative 12. And then on the right-hand side, when I put a 0 in, I get negative 6. Negative 12 is indeed less than negative 6. So that interval has a truth value of t, which is true, which means that that interval is part of the solution. I'm going to put 6 in and see if my actual point, my critical number 6, works. So when I put a 6 in, let's just test 6 right here. When I put a 6 in, I get 3 times 2, which is 6, is less than or equal to 2 times 6 is 12. 12 minus 6 is 6. So when I plug a 6 in, I'm going to make this really colorful here. I get 6 is less than or equal to 6, which is true. So 6 is included. I'll just put a closed circle on 6. Now I need to test a value between 6 and infinity. So let's maybe choose 10. When I put 10 in, so I'm going to try 10. When I put 10 in, I said it was going to be very, very colorful. 3 times 6, 10 minus 4 is 6. 3 times 6 is 18. Is less than or equal to, again I'm putting 10 in, 2 times 10 is 20. 20 minus 6 is 14. This is false. So if I put a value in between 6 and positive infinity, that truth value is false, which means that interval does not work. So this, I know this seems the long way of doing this. You're like, why could I not just say x is less than or equal to 6? You can say x is less than or equal to 6. But what I'm trying to show you is what you're going to have to do when we get to polynomials that are not linear in nature. So let's come over here and I shall show you. So here we have a third degree polynomial is greater than 0. Our first step is to find the critical numbers, and the critical numbers are the zeros. So we have x equals -3 and x equals 1. I'm going to create a number line, and I'm going to test each interval, and I'm going to test each critical number as well. So we have -3 to the left of +1, so I have 3 intervals to test. If I put a -10 in, so I'm going to test -10. When I put a -10 in, -10 plus 3 is a negative number. -10 minus 1 is a negative number squared. And I need to see if that's greater than 0. Well, a negative times a negative times a negative is a negative, and a negative result is never greater than 0. So that interval is false. When I put a -3 in, -3 does not work. -3 plus 3, -3 plus 3 is 0. 0 times anything is 0, and 0 is not greater than 0, it's equal to 0. Now let's try between -3 and 1. If I try between -3 and 1, I'm going to test maybe the value of 0. When I put a 0 in, 0 plus 3 is positive, 0 minus 1 is negative, and then that value is squared, is greater than 0. Well, a positive times a negative is a positive, and positive numbers are always greater than 0. That has a truth value of t. Now I'm going to try 1. When I put a 1 in, 1 minus 1 is 0, and 0 squared is 0, and anything times 0 is 0. So 1 does not work because 0 is not greater than 0. Now let's try the interval from 1 to infinity. I'm going to try 10. So I put a 10 in. 10 plus 3 is positive. Okay, then 10 minus 1 is also positive, and then when you square that, positive numbers are all greater than 0, therefore that has a truth value of t. So our answer is, I'm going to use a highlighter to show the answer. The answer is the interval from -3 to 1, to +1, with open interval, and then from 1 to infinity with an open interval. So our answer is -3 to 1 and 1 to infinity, and it's all open intervals. This, or some people write the union symbol in place of the comma. Either one of those forms would be correct. Now, if you already know how to graph polynomial functions, you may be there, you may not. If you are already there where you can graph polynomials, you're going to see that at -3, we have a multiplicity of 1. So our graph is going to go through that 0, that root, that x-intercept. And at +1, that is a multiplicity of 2. So it's going to bounce off. So something like this is going to happen in your polynomial. So you can see from -3 to +1, we have positive outputs, right? And then from 1 to infinity, we also have positive outputs. So hopefully that kind of gives you an idea graphically of what's happening. If you're not yet there graphically, when you get there graphically, you can apply that to our polynomial inequalities. So here's one for you to try. So you can try this, press pause. I'm going to work it out. So if you just want to try this on your own, make sure you press pause. If you want to follow along, see if you've got it. You might need to press pause a little bit because I might go a little bit fast here. I'm going to get my inequality so that I have 0 on one side, please remember to do this. I'm going to factor. I'm going to continue to factor. And then I'm going to take each variable factor and apply the zero product property. Now the yellow and the green produce critical numbers of 0 and 1, but this blue does not produce real numbers. So we don't get any real numbers when we try to use the quadratic formula there. So my critical numbers, 0 and 1, create 3 intervals. Now when I subtracted x from both sides, that created an equivalent inequality. When I factored, that also created an equivalent inequality. So when I test these values, for instance, I'm going to test, let's just say, -2. When I test -2 in the interval from negative infinity to 0, I'm going to have a negative number. So I put a negative in there. And then when I take -2 and multiply it by itself 3 times, I get -8 minus 1, which is also a negative number, is less than or equal to 0. Well, a negative times a negative is not less than 0. This is false. So that's a big fat false. When I put 0 in, 0 times anything is 0. 0 is going to be included this time because of the equal sign. In fact, 1 is going to be included as well, because when I put a 1 in, one of my factors will be 0, and 0 is equal to 0. So I'm going to put closed circles right there. Now I'm going to need to try 1/2. This is why I use just symbols, signs, negative signs, positive signs, rather than the actual numerical value. So we're testing between 0 and 1. So we're testing between 0 and 1. Does that interval work? When I put a 1/2 in, 1/2 is positive. I'm using this equivalent inequality right here. When I put a 1/2 in to my second factor, 1/2 cubed is 1/8. 1/8 minus 1 is negative, and a negative times a positive is definitely less than 0. That is true. So I put a true right there. Now I'm going to test between 1 and infinity. Maybe I'll use 10. That's very obvious, right? 1 to infinity. 10 is positive. 10 cubed minus 1 is also positive. That cannot be less than 0. Therefore, that part's false. So our only solution here, our only solution is between 0 and 1. Inclusive. Okay, rational inequalities. Rational inequalities are interesting because rational inequalities just have a little bit of a difference. So let's just be very clear where we're going to get our critical values from. Values that make the numerator 0. Values that make the numerator equal to 0 are critical values. I'm saying values, but I'm also going to write numbers because it's shorter. So values that make the numerator 0 are critical numbers, and then additionally, domain restrictions. Domain restrictions are critical numbers. So what would our critical values be here? Our critical values would be 1 from the numerator. I should write that in red so it's color-coded. And then from the denominator, x equals +2 and -2. And +2 and -2 are completely restricted, so those are going to be open circles. So I'm going to have -2, +1, +2. 1, 2, 3, 4 intervals. And I know that -2 and +2 are going to be open circles because they are completely restricted. Will 1 work? When I put a 1 in, 1 minus 1 is 0 in the numerator with -3 in the denominator. 0 over -3 is 0, and 0 is equal to 0, so 1 is going to work. So you just test that critical number in there, and now we can test each interval to see which interval of solutions works. So from -infinity to -2, and I'm going to come over here and I'm going to write this, x minus 1 over x plus 2, x minus 2 is greater than or equal to 0. And I'm going to use those signs again. If I put -10 in, when I put a -10 in, I get a negative number in the numerator. In the denominator, -10 plus 2, -10 plus 2 is negative. -10 minus 2 is negative. A negative over a positive results in a negative. Is a negative greater than or equal to 0? That is false. Okay, let's try a number between -2 and 1. Let's try 0. When I put a 0 in, 0 minus 1 is negative. I'm coming back over here. 0 minus 1 is negative, over 0 plus 2 is positive. 0 minus 2 is negative. A negative over a negative is a positive, and a positive will always be greater than 0. So that is true. Now we're going to try a number between 1 and 2. Let's try 1.5. 1.5 minus 1 is positive in the numerator. 1.5 plus 2 is positive. 1.5 minus 2 is negative. That's going to result in a negative number, and a negative number is never greater than 0. Therefore, that interval is false. And then we're going to try 10. If I put a positive 10 in, 10 minus 1 is positive. 10 plus 2 is positive. 10 minus 2 is positive. All positive numbers are greater than 0, so that is true. So our interval of solution would be -2 with an open interval to +1 with a closed interval, and then 2 with an open interval to infinity. So -2 to +1, and then 2 to infinity. Now there's one more problem that could get tricky. Remember that we need 0 on one side of our inequality. I'm going to subtract the fraction from the right over to the left, and then I'm going to have to get a common denominator. So I'm going to multiply the first fraction by x minus 3 over x minus 3. And I'm going to multiply the second fraction by x minus 2 over x minus 2. That's going to give me a common denominator of x minus 3, x minus 2. And then in the numerator, I have x minus 3 minus 2 times the quantity x minus 2. So minus 2 times the quantity x minus 2. So that's going to give us x minus 3 minus 2x plus 4 all over x minus 3, x minus 2. Still have a little bit of simplifying to do. We've got -x plus 1 over x minus 3, x minus 2. My critical number from my numerator is x equals 1. If I put a 1 in, I get a 0. My restrictions from my denominator are x equals 2 and 3. So on a number line, I have 1, 2, and 3, where 2 and 3 are complete restrictions, so those are open circles. When I put a 1 in, I get 0 is less than 0, And that is not true, so that is also an open circle in this case. Now I need to test each interval, and I'm going to use this form. This is an equivalent form. I'm going to use this form to test. And the reason I'm doing that is because it's going to be easier for me to just test my intervals with the signs, S-I-G-N-S, the signs positive and negative, using the factored form. So if I put in a 0, that's going to be between negative infinity and 1. If I put a 0 in, I'm going to get a positive, let's show our workout over here. I'm going to get a positive over a negative times a negative, which is a positive. And I want to be less than 0. So that is going to be false. Now let's try 1.5. So I might run out of colors here. I'm going to try to be creative. 1.5. So if I try 1.5, remember I'm coming back here. Negative 1.5 plus 1 is negative over 1.5 minus 3, that's negative. 1.5 minus 2, that's negative. A negative over a positive is a negative, and a negative is always less than 0, that's true. Let's try between 2 and 3. Let's try 2.5. Let's use a different color. 2.5. Negative 2.5 plus 1 is negative. Negative 2.5 minus 3 is also negative. 2.5 minus 2 is positive. So a negative over a negative is a positive. A positive is not less than 0. That's false. And then we get to try a number between 3 and infinity. Let's just try 4. Change things up. When I put a 4 in, the opposite of 4, this is where I'm coming right here. The opposite of 4 is negative 4, right? Negative 4 plus 1 is negative over 4 minus 3 is positive. 4 minus 2 is positive. A negative over a positive is a negative. And negatives are always less than 0. That's true. So we have an interval, I love using this highlighter, from 1 to 2, and it's an open interval, and then from 4 to infinity. So 1 to 2, open interval, and then I said 4 to infinity, but I meant 3 to infinity. 3 to infinity. That critical number is 3.